Okay, I would like to talk to you briefly about uh, glasses and the way the composition of the glass affects its properties, mainly its melting point, but also its chemical stability. And that's related to how many metal ions besides silicon we have in the structure. So if it's a glassy ceramic, it's a fairly safe bet that it's going to be a silicate material with silicon and oxygen. However, we can add other metal oxides to this material. For example, potassia, sodia, or calcia. And in case you haven't heard it before, the shorthand that I'll be using is very common in material science. It makes the oxides easier to pronounce quickly. If we have a oxide between potassium and oxygen, potassium oxide, for example, then we can say the name of that as potassia. So we remove the oxide and the end of the element name of the potassium and we replace it with Ia. And that tells us that it's the oxide of that metal. So sodium oxide would be sodia. Calcium oxide will be calcia, and you'll hear me use that throughout the ceramic section with increasing frequency. Okay, so the important thing about these network modifiers that we can add is that they come from the far left side of the periodic table of the elements. Sodium has a +1 charge on it. I'm sorry, potassium, so does sodium. Calcium has a +2 charge. And so all of the elements used in this example of network modifiers come from column 1, the alkali elements, or column 2 of the periodic table, the alkaline earth. And there are a lot of others that we could have used from those columns, and they would also count as network modifiers. And the effect of adding those elements from columns 1 and 2 is that they come in and they break up the structure. For every one of those that you add instead of a silicon cation, then we have less bonding in the network, and that weaker bonding and looser structure decreases the refractoriness of the material, makes it easier to melt, easier to process, but it also decreases the chemical stability somewhat. But these materials still tend to be very chemically stable unless we add more than 50% of network modifiers to the material. And we have another class of additives we can put in glasses called intermediates. And the intermediates don't have the +4 charge of the silicon, but they do have more than the charge of the alkali and alkaline earth network modifiers. Aluminum is +3, boron is +3, so they're kind of in between. And intermediates, as the name implies, can act sometimes like a network former and sometimes like a network modifier. It depends on how much of them are added and how many network modifiers are already in the composition. If a small amount of an intermediate is added, then it will act as a network former. Then beyond a certain point, it begins to break up the network. So everything we've discussed so far is in terms of modifying the melting point of glasses. A similar effect is seen if we add network modifiers and intermediates to crystalline silicate materials instead of glassy silicate materials. However, the structures that are formed in crystalline silicates are very complicated in terms of the mathematics of the composition, and their differences don't impact your future knowledge that you'll need for dental ceramics in subsequent courses, and so they're beyond the scope of this course to learn about. Okay, we talked about chemical resistance of ceramics, and I want to talk a little bit more about chemical resistance in terms of resisting acids and bases this time. And so how easy is it to dissolve a ceramic? We mentioned that most ceramics that we deal with, oxides, especially silicate oxides, tend to be quite stable. But why would we want to dissolve a ceramic? We would want to dissolve it if we wanted to just roughen up the surface to make a stronger bond to another material that we want to attach the ceramic to, whether that's another ceramic or whether it's a metal, whether we're repairing two ceramics by attaching them with a polymer-based repair cement, or whether we're cementing them onto a tooth surface. And so very useful for bonding to roughen the surface. And so silicates and non-silicates behave differently in respect to being able to dissolve them. For silicates, first of all, we have a special situation whenever we have acidic conditions or low pH, and we also have fluoride at the same time. If those two are present, we will have rapid dissolution of silicate ceramics. That's because the silicon and the fluorine ions react together to make a complex ion, silicon hexafluoride ion. And whenever ions in solution can react with each other to make a complex ion, it effectively decreases the concentration of those single ions in solution by themselves, which leads to more of those ions dissolving from the solid into solution. So this presence of the fluorine and the acidic pH allows that complex ion to form and makes the glass dissolve rapidly. But if we have acidic pH by itself and no fluorine present, then we will get very slow dissolution of the glass. If we go to high and alkaline pH, then we again get rapid dissolution, but this is rarely encountered. It's not encountered in the human body, and it's rarely encountered in chemical processing in the laboratory. So this situation is not common at all. The other two situations are more common. And one that's important to remember is the fluoride, because fluoride treatments are used in dentistry. We can avoid having acidic pH and fluoride present at the same time by using a neutral fluoride whenever we have ceramics in the patient's mouth. However, hydrofluoric acid has acidic pH and fluoride ions together, and that is used on purpose as an acid gel to etch ceramic restorations in dentistry. For the non-silicate materials, which also tend to be polycrystalline or 100% microscopic crystalline material, known as polycrystalline. Those are resistant to dissolving in all types of acidic or alkaline media. If you would like to roughen the surface for some reason, like cementing them to another material, then you have to use sandblasting, which is these days known as airborne particle abrasion. That's what we used to call sandblasting. Fancy name for sandblasting. And there are polycrystalline ceramics such as zirconia, which is zirconium oxide, for which it was recommended for a long time not to use sandblasting on them. That was thought that it would weaken the material, and now manufacturers have realized that sandblasting can be used on zirconia as long as it is done very lightly and carefully, and then it can actually form a stronger material and a rough surface that's easy to bond to. So one of the important differences between ceramics and other materials was that ceramics are much harder. And we can see on the graph here, you will see me use these types of graphs several times. And when I do, the yellow bars indicate the range in material property. In this case, Vickers hardness number is the material property. And the range is going from the least hard, commonly used ceramic material to the most hard, commonly used ceramic material. And I'm comparing that with the least to the hardest in terms of metal and polymers. So that's the range that we typically encounter in material properties. And in the case of tooth material properties, you will typically have dentin on the bottom line of the graph and tooth enamel on the top of the graph there. So that's a range for teeth. Ceramics are much harder compared to other materials we have. We mentioned that gives them superior wear resistance, but it can make them an abrasive antagonist, means they can wear away other materials accidentally. And whether or not they do doesn't have to do with just how hard they are compared to the other material. It has to do with how smooth the surface is. If you have a very hard material, but it's very smooth, then it won't wear away opposing materials. So if the surface is polished, not rough, we mentioned the ceramics are composed of microscopic crystals. If those crystals are small enough, then there will be less abrasion. And if there are pores in the material, then that will make the polished surface rough because it will have lots of holes in it. And porosity will lead to increased abrasion. And this is a very strong effect, as the graph on the right can show you. This is a graph of, it has different ceramic materials that have rubbed up against bovine enamel, cow tooth enamel, and the bar in the middle here is the wearing behavior over time that a natural cattle tooth has against another natural cattle tooth. So that's kind of in the middle of the range. And over here we have ceramics that wear away cattle teeth quickly, and down here we have ceramics that wear away cattle teeth very slowly, even less slowly than other natural teeth. And the difference is not the hardness of the material. In fact, some of the worst offenders have the lowest hardness. The reason that they're the worst offenders is they have the highest porosity. So these two materials here are more porous, definitely more porous than the glass ceramic materials here. We'll talk more about that at the end of the ceramic section of the course when we talk about processing methods, why some of those materials end up more porous than other ceramic materials. But for now, understand that it's not the hardness, but the presence of the pores in combination with the hardness that wears away opposing natural dentition.